Have you ever, really looked at the universe's building blocks and just wondered, why three?
Mm.
Not just one type of particle, but these three distinct families. It's almost like cosmic nested gulls, right? And each one gets heavier, less stable. I mean, for decades, the standard model of particle physics has done a brilliant job cataloging these generations, the quarks, the leptons. But it's been, well, pretty quiet on the big why. Why are there three? Why the increasing mass? Why do the heavier ones just poof, decay? These are the kinds of questions that really keep scientists up at night. So today we're taking a real deep dive into a pretty fascinating new theoretical idea, a framework that actually proposes a solution. And it's a solution that, well, it goes way beyond our usual four dimensions. We're going to be talking about some really mind-bending stuff, concepts like hypergravity and this totally new idea called coherence coefficients, things that could honestly rewrite how we understand matter itself.
Yeah, and what's really groundbreaking here, I think, is that this new framework, the HHHCR-ToE, it suggests these generations aren't just, random copies, not some cosmic accident. No, it suggests they're deeply tied to how coherent a particle is.
Coherent. Coherent with what?
With a higher dimensional gravitational field. The theory calls it hypergravity. You can almost picture it like this, this fundamental hum running through the universe, maybe in hidden dimensions. And particles either resonate really strongly with that hum or they don't. And that resonance, that coherence, basically dictates their whole nature, their mass, how stable they are, everything.
Okay, wow. So get ready to stretch your mind a bit here. We're going to unpack the standard model's big unanswered questions, introduce these really revolutionary concepts, and then we'll use them to try and explain, well, everything from why electrons are so stable and dependable to what a hypothetical particle get this ring, maybe 23 TeV.
Which is enormous.
Absolutely enormous. And existing for less than a millionth of a trillionth of a second, what that might actually mean for physics. Okay, let's uncheck this. Let's dive into the universe's hidden generations. Right, so let's start with what we do know. Let's ground ourselves first. The standard model, it's our best theory, incredibly successful, describes the fundamental bits and pieces of everything. And it tells us about quarks and leptons. These are the truly elementary particles. But crucially, it shows they aren't just a jumble, they're organized into three distinct families or generations. And this repetition, this pattern of three, that's really key to the whole mystery we're digging into today.
That's exactly right. Each of these three generations is like a complete set, almost a mirror image of the others in some ways. Each one has two quarks and two leptons. And the particles within a generation, they share fundamental quantum numbers. They interact via the weak force in similar ways. But, and this is the kicker, they differ hugely in mass.
Yeah.
So let's look at the first generation. This is the stuff of, well, everyday matter, our world. You've got the up and down d quarks. These guys stick together to make protons and neutrons, the part of atoms.
Our basics.
Exactly.
Yeah.
And then the leptons, the electron orbiting the nucleus, making chemistry possible. And the electron neutrino, which is super light, barely interacts with anything. These are, as the source says, the lightest and most stable particles. The electron neutrino, trillions just zip through you every second. Basically ghosts.
They really are the definition of stable, aren't they?
Now, move up to the second generation. Here, things get, well, heavier and less stable. You've got the charm, C, and strange quarks.
Yeah.
And the muon neutrino. And the crucial point is these are heavier than their first-generation counterparts and are less stable, decaying into first-generation particles after a short time.
Like the muon, right? The fat electron.
Exactly. The muon. It's about 200 times heavier than an electron, but it doesn't hang around. It decays really quickly into an electron, a muon neutrino, and an electron antineutrino. And this process, this decay, where heavier particles just shed mass to become lighter ones, that's a central puzzle. The standard model sees it, describes it, but doesn't explain why it happens. And finally, the third generation. This packs the top T and bottom B quarks, plus the tau lepton and the tau neutrino. And no surprise here, these are the heaviest and least stable of the lot.
Especially the top quark. That one's famous for being massive.
Oh, absolutely. The top quark is just extraordinary. It holds the title, the most massive fundamental particle observed in nature. It weighs about as much as a gold atom, which is just wild for a single fundamental particle.
Incredible.
And like its third-gen buddies, it decays rapidly into lighter particles. It exists for just the briefest instant before transforming.
Yeah.
These third-gen particles are like fleeting whispers in the grand scheme of things.
And what's really powerful, what makes the standard model so convincing, is that this whole structure, these particles, these families, it's not just theory, it's been confirmed. over and over again. Decades of really careful, hard experimental work, we've actually seen the evidence.
Absolutely. The experimental backing is incredibly solid. You can't argue with it. Take the leptons. The muon discovery was actually a surprise way back in the 1930s. Nobody expected it. Then the tau turned up in the 1970s, so that proved the electron wasn't alone. It had these heavier, unstable siblings. And the neutrinos that go with each of them, those were pinned down later through all sorts of tricky, weak interaction experiments. That really sealed the deal on the complete lepton families. And the quark story, just as compelling. The charm quark, for instance. It was predicted theoretically in 1970 to explain some weird experimental results.
To make the math work out.
Pretty much. And then, boom, 1974, it's discovered experimentally. They found this particle called the JC meson, and there it was, vindication. The top quark hunt was even more dramatic. It took decades, huge teams, massive machines.
A real chase.
A global chase. Finally nailed down in 1995 at Fermilab's Tevatron. These weren't easy discoveries, but each one was a vital piece locking the Standard Model's generational picture into place. And it's not just finding the particles directly. We also have really strong indirect evidence telling us there were likely only 3 generations. For example, experiments with flavor-changing neutral currents and neutrino oscillations provided indirect evidence that there are only 3 generations.
Neutrino oscillations, that's where they change type as they travel, right?
Exactly. Neutrinos morphing from one flavor electron, muon, or tau into another. It shows they're all interconnected. And these kinds of experiments, along with others looking at rare particle decays, strongly suggest that, well, 3 is the magic number. There probably aren't more stable generations hiding out there.
Okay, so we've got this incredible theory, the Standard Model. It describes the 3 generations, their masses, how they decay. It works beautifully. It's one of science's biggest triumphs. But, and it's a big but, despite all that success, it leaves us hanging with some really basic fundamental questions. It tells us what happens with amazing precision, but it's completely silent on the why.
Precisely. That's the wall the Standard Model hits. It's a fantastic description, like an incredibly detailed map. But it doesn't explain the underlying geography, why the landscape is shaped the way it is. It has these limitations when it comes to deeper explanation. So first, the really obvious one. Why 3 generations? The Standard Model just doesn't say. As the source puts it, it does not explain why we observe 3 and not more or fewer generations. It only models what we see experimentally.
It just takes 3 as an input from nature.
Exactly. It's like having a recipe that works perfectly, always makes 3 cakes, but you have no clue why it's not 2 cakes or 4. The number 3 is just there, an observed fact baked in. Then you've got the mass hierarchy, which is just baffling, really. The masses of the particles increase as we move from the first to the third generation, but there is no explanation for this mass hierarchy.
And it's not just that they get heavier, it's how much heavier. The range is enormous.
Right. You go from nearly massless neutrinos to the top quark, which is, as we said, like a gold atom. It spans orders and orders of magnitude. Now, the Higgs mechanism explains how particles get mass by interacting with the Higgs field. It's a huge discovery. But it doesn't explain why the masses are distributed like this. Why this specific, steep, kind of weird pattern across the generations, that pattern itself is a deep mystery. And finally, the decay pattern. Why do heavier generations decay into lighter ones? The Standard Model says heavier particles are unstable and decay into particles from the lighter generations, but the reason behind this decaying structure is not fully explained.
We know how they decay, the rules they follow.
We can calculate the probabilities, the lifetimes, very accurately. But the fundamental drive behind it, why this inherent instability? Why the relentless push towards decaying into those lighter, stabler first-generation forms, that's still a black box. And, if you connect this to the bigger picture, these aren't just minor loose ends. These are significant gaps. They really point towards a missing piece in our fundamental understanding of reality. And that's exactly where new ideas like this HHHCR-ToE theory try to step in.
Okay, so this is where we really start venturing beyond the familiar territory of the Standard Model. The HHHCR-ToE, the HHHCR theory of everything. It's a pretty ambitious name, right?
It certainly is.
And it's this bold framework that, as you said, goes beyond the Standard Model. It proposes a much deeper reason for these particle generations, and it connects them to these really wild ideas: hypersymmetry, hyperfractal geometry, and coherence resonances. It's basically suggesting the answers aren't just here in our everyday space-time, but hidden in something much bigger, maybe higher dimensions.
Indeed. The HHHCR-ToE introduces several key concepts. foundational ideas that directly link particle properties to these proposed higher dimensions, and they completely reshape how we might think about particles. Understanding these is, well, absolutely crucial to seeing how the theory tackles the generation mystery. So first up, there's hypergravity, GH. The theory defines this as the higher dimensional gravitational field within the HHHCR-ToE framework. Think of it as the fundamental gravity acting in this larger hyperspace, going beyond our familiar 4D space-time gravity.
So not just the gravity holding planets in orbit, but something more fundamental, operating in extra dimensions.
It's proposed as the overarching gravitational force in these higher dimensions, and it's intimately tied to how all particles behave at their most basic level. Next, and this is really central, maybe the core new idea is the coherent coefficient C. This is a new quantity the theory introduces. It quantifies the degree of coherence or resonance between a particle and the hypergravity field, and it's a number between 0 and 1.
Okay, coherence with hypergravity, like how well they're in sync.
That's a great way to put it. If C equals 1, that's perfect coherence. An example given is photons, which have 0 mass. They're perfectly in sync, perfectly resonant. But if C is less than 1, that signifies less than perfect coherence, and that's the state for all massive particles. The lower this C value, the less in sync, the less coherent the particle is with this hypergravity field. Then there's something called the resonance operator.
R. You could maybe think of this like a mathematical tool, a cosmic tuning fork, almost. It describes the coupling between quantum fields and hypergravity. It basically quantifies that resonance, that coherence we were just talking about. It governs properties like mass and stability by defining how strongly a particle resonates. It's the bridge, mathematically speaking, between the particle's field and hypergravity. The theory also talks about degrees of freedom. In physics, that usually means the number of independent ways a system can change.
Right, like position, momentum. Exactly. Here, it's defined as the number of independent parameters, quantum states, that define the state of a particle. And the theory makes a key claim. Higher degrees of freedom are associated with higher mass and lower coherence. So intuitively, maybe more internal complexity, more ways a particle can be at a quantum level. This maps to being heavier and also less stable, less coherent. And a really critical dynamic process in this model is coherence collapse. This describes a sharp decrease in a particle's coherence with hypergravity. It's not gradual. It's triggered by the decay of its resonance, and it leads directly to increased mass and instability.
Like falling off a cliff, coherence-wise.
Pretty much. A sudden dramatic plummet in how well the particle resonates. Think of it like a structure suddenly failing, leading to immediate consequences for its mass and stability. And lastly, there's hyperfractal scaling. This points to the nonlinear fractal nature of the underlying hyperdimensional geometry.
Fractal, like those patterns that repeat at different scales.
Exactly. It suggests that the geometry of this hyperspace isn't smooth, but have this intricate, self-similar structure. And this fractal nature directly influences how coherence and mass change between generations. So the very shape of these hidden dimensions might be dictating the patterns we see in particles.
Wow, okay. That's a whole new vocabulary: hypergravity, coherence, collapse, fractals. It's a lot. So how do these pieces actually fit together? How does the HHHCR-ToE use these ideas to explain why we have particle generations in the first place? What are the possibilities it puts forward?
That's the million-dollar question, isn't it? And the theory offers several related possibilities, but they all circle back to this central theme of hyperdimensional coherence. One idea involves hypersymmetry and dimensional embedding. Here, the different generations could be thought of as different states or modes of hypersymmetric structures within higher dimensional spaces. End quote. These different states might emerge when the initial perfect symmetry of hyperspace breaks, maybe as extra dimensions curl up or compactify into the 4 we experience.
So generations are like echoes of lost symmetries from higher dimensions.
That's one way to look at it, yeah. Another possibility is rooted in fractal hierarchies and resonance. This suggests that the hyperfractal nature of our framework means the 3 generations reflect distinct resonance harmonics of fundamental fields. Imagine it like musical notes, a fundamental tone and its overtones. Each generation could correspond to a different harmonic resonance within this hyperfractal structure, and that frequency dictates its properties.
Like different notes on a cosmic guitar string.
Kind of, yeah. A nice analogy. Different vibrational modes leading to different particles. Then there's the idea of hyperdimensional coherence patterns. In this view, generations are seen as an emergent property of coherence, coupling between quantum fields and hypergravity. They might be distinct stable patterns of resonance within some kind of vast interconnected network, a coherence conduit network running through hyperspace. Each generation is a particular stable configuration in this network, and a final angle connects to symmetries again, but slightly differently, a gauge symmetry continuum. This suggests generations might represent different stages of symmetry reduction, aligning with specific steps as symmetries break down, starting from some ultimate hypersymmetry and eventually leading to the familiar symmetries of the standard model. So at the end of the day, what all these possibilities point to is that the HHHCR-ToE connects the existence of particle generations to these really deep principles: hyperdimensional coherence, fractal structures, and the way symmetries break down in higher dimensions. It's arguing that the pattern we see the three generations isn't just random. It's fundamentally baked into the fabric of hyperspace itself, a reflection of its geometry and its resonant properties.
Okay, this feels like we're getting to the real core of it now. The HHHCR-ToE isn't just throwing out new terms, it's trying to weave them together into a single story that explains the generations. And your explanation really hinges on this coherence coefficient, doesn't it? Tying the three generations directly to that, offering a way to understand the mass differences and why they behave the way they do.
Exactly. The framework makes this connection very explicit with a central hypothesis. It proposes a clear coherence ranking. What this means is, first-generation particles have the highest coherence with hypergravity. They're the most in sync. Second-gen are intermediate. And third-gen have the lowest coherence, the weakest resonance. And flowing directly from that ranking comes the really crucial mass and incoherence relationship. The theory states the mass of a particle is inversely related to its coherence coefficient. A higher coherence implies a more stable, less massive particle. As coherence decreases, mass increases. M1c.
So less coherence equals more mass. Simple as that.
Fundamentally, yes. That's the proposed direct link. Strong coherence means light and stable. Weak coherence means heavy and unstable. It paints a picture where mass isn't just something particles have, but rather a consequence of their imperfect resonance with this underlying hypergravity field, and then immediately gives us an explanation for instability and decay. Particles in the second and third generations, being inherently less coherent, are therefore more unstable. Because they exist in this less coherent state, they naturally seek more stable, more coherent states. It's like they're inherently driven towards better resonance.
Which means decaying into first-generation particles.
Precisely. So the theory views decay as a coherence transition. The process of decay is seen as a transition toward higher coherence. During decay, mass decreases and coherence increases. This beautifully explains why we always see heavier particles decay down to lighter first-generation ones. They are, in a sense, striving for that most coherent, most stable state available to them. And we can use the photon as a perfect illustration here. In our framework, photons have a perfect coherence coefficient C10. They couple perfectly with hypergravity, and what's the consequence? Thus, they possess no mass. It fits perfectly with the core idea. Mass only arises from imperfect coherence. Perfect coherence means zero mass. There's also a useful analogy mentioned in the source material to help visualize this. Our analogy with the relativistic effects of speed on quantum fields encountering hypergravity is useful here. Think about special relativity. As things approach the speed of light, their effective mass increases, like moving faster creates more resistance.
Right. Mass increases with velocity?
Yeah. And the analogy here is that as particles become more incoherent, their mass increases, just as relativistic particles experience increased mass from hypergravity drag. So you can almost picture incoherence as a kind of drag or resistance the particle experiences as it moves through or interacts with hyperspace. And this drag manifests directly as mass.
Okay, that's a really compelling picture for why the masses climb so steeply. It makes intuitive sense in this framework. But it still leaves that big standard model question hanging. Why stop at 3? Why only 3 generations? Why not 4, 5, 6? Is there some kind of ultimate limit built into this coherence idea?
Yes, absolutely. And the HHHCR-ToE proposes a specific mechanism for this limit, the incoherence threshold. The idea is that the third generation represents the maximum limit of incoherence possible in particle physics. Beyond this point, particles become too unstable to exist as distinct entities. There's essentially a tipping point, a fundamental boundary. If a particle is too incoherent, it just can't hold itself together long enough to even be considered a particle in any meaningful sense. So the reason we don't see a stable fourth generation, it's because particles with coherence coefficients even lower than the third generations, well, they'd be past this threshold. They would be so incoherent that they would instantly decay into more coherent states, making it impossible to sustain a stable fourth generation.
They just vanish immediately.
Almost instantaneously. Too fleeting to observe, too unstable to exist as a persistent state. And the theory points to the top quark as our best real-world example of something right at this boundary. The heaviest known particle, the top quark, with a decay time of about 5 seconds.
Which is just unbelievably short.
Mind-bogglingly short. It's the shortest decay time of any known particle. It's practically ephemeral, so the top quark's very short lifetime and high mass make it an excellent candidate for defining the incoherence boundary. Its coherence coefficient, whatever that value turns out to be, C, essentially marks the lower bound of coherence. Any hypothetical particle with even lower coherence would decay even faster, possibly too fast to measure. This reinforces that direct link. Lifetime is proportional to coherence, C. Lower coherence means a dramatically shorter lifetime, plummeting towards zero at that threshold.
So it sounds like these transitions aren't smooth at all. Particles don't just gently slide from one generation to the next. It's more like a series of dramatic, sudden shifts. How does that actually happen in this coherence hypergravity picture?
You're absolutely right. It's portrayed as anything but gentle. The driving force is resonance decay as the trigger. The transition between particle generations occurs when a particle's resonance with hypergravity decays. That fundamental hum we talked about. When a particle's ability to resonate with it weakens significantly, things change drastically. This weakening leads directly to decreased coherence, increased mass, and instability. And crucially, this isn't a gradual decline. It involves the sudden coherence collapse at thresholds. Coherence collapse occurs when resonance decays to a certain threshold. These thresholds are described as nonlinear, meaning not smooth, not proportional. Exactly. The change in coherence is not smooth or gradual, but occurs sharply at critical points. Think of it like phase transitions in matter, water to ice, for example. A small change in conditions can trigger a massive sudden change in state. The nonlinear nature may be represented by some mathematical function where coherence drops off a cliff as resonance hits these critical points that could explain why transitions between generations are sharp and why mass increases significantly as coherence collapses. It's a jump, not a slope. So we can visualize this with a resonance decay model. For the jump from the first to second generation, the particle's resonance decays to a specific threshold. Let's call it RO. This triggers a nonlinear jump, a coherence collapse. The particle suddenly becomes much more massive and less coherent. Then for the second to third generation transition, resonance decays further, hitting another critical threshold, R. This causes another, perhaps even more dramatic, coherence collapse. And now the particle is near the incoherence boundary, super heavy, incredibly unstable, right on the edge of existence. But it's important to note that between these sudden sharp transitions, the theory suggests there are regions of relative stability, these coherence plateaus. The first plateau, that's where you find high coherence, low mass. Stable particles like the electron live here. The second plateau, intermediate coherence, intermediate mass. Think of the muon. Relatively stable compared to the third gen, but not forever. And the third plateau, this is characterized by low coherence, high mass. Particles like the tau, and especially the top quark, exist here. They're balanced on the edge of incoherence, just before that final threshold. Now, you might wonder how this connects to symmetry breaking, which is such a key concept in particle physics, like with the Higgs mechanism.
Yeah, is this related?
Well, the HHHCR-ToE suggests symmetry breaking might occur as a secondary effect of coherence collapse. As a particle loses resonance and its coherence drops, it simultaneously loses some kind of symmetry with respect to the hypergravity field. And this loss of hyperdimensional symmetry is what leads to increased mass and instability. But the source clarifies this process might not be directly related to traditional gauge symmetries, like those in the standard model. It could involve hyperdimensional symmetry breaking mechanisms unique to our framework. So it's a different kind of symmetry breaking, happening at a deeper, potentially higher dimensional level. And finally, let's bring hyperfractal scaling back into the picture. Remember the idea that hyperspace might have a fractal geometry. This suggests the three generations reflect distinct resonance harmonics of fundamental fields, maybe tied to that fractal structure. And the sharpness of the phase transitions, those sudden coherence collapses, they could correspond to fractal discontinuities or critical points where resonance with hypergravity suddenly breaks down. So the very intricate, repeating geometry of hyperspace might be the underlying reason for these sudden, dramatic jumps between generations.
Okay, this leads us into some really wild, speculative territory, but it's super exciting. The idea of a fourth generation. If the third generation is right at the edge of coherence, right at that instability limit, does this HHHCR-ToE model actually allow for something beyond that? Like, could there be a fourth generation that's just so unstable we haven't seen it, maybe can't even observe it directly?
That's a fantastic question, and yes, the framework is actually consistent with that idea. As the source states, the hypothesis of a fourth generation existing for an extremely short time frame is consistent with this framework. If particles existed with coherence coefficients even lower than the third generations below that CF boundary marked by the top quark, they would have such a weak coupling with hypergravity that they would decay almost instantaneously.
So hyper unstable.
Exactly. So incredibly incoherent. Their existence would be measured in maybe yoctoseconds or even less, vanishing practically before they even fully formed.
Wow. Okay, so if they could exist even for an instant, what would they be like? And this is where your work gets really specific, making these bold predictions. That 23 TV mass figure is really striking. How does the framework even allow for such a precise prediction? And you mentioned there were different ways to get to that number.
Right. The convergence of results from two different lines of reasoning within the theory is what makes the 23 TV estimate particularly compelling. Let's walk through them. Method 1 is what we can call the plateau approach, based purely on mass scaling observed between known generations. We look at the quarks. Going from the tiny up quark, 2.2 MeV, to the charm quark, 1.28 TeV, the mass jumps by a factor of about 581. Then going from charm to the huge top quark, 173 GeV, the mass jumps again, this time by a factor of about 135.
Okay, so the factor decreases, but it's still a big jump.
A very big jump. Now, the simplest extrapolation is to assume that this factor of increase we see between the second and third generation, that factor of roughly 135 might continue or at least be indicative of the next step from the third to a hypothetical fourth generation. If we apply that factor to the top quark's mass, right, fourth gen quark, a quantity of 30,000 GeV or 23 TVA, a truly staggering mass.
23 trillion electron volts.
Yep. For comparison, the LHC currently collides protons at about 13.6 TeV as center of mass energy. So we're talking about a particle potentially much heavier than the collision energy we routinely achieve now. We can do a similar exercise for leptons, though the factors are different and smaller. Electron to muon is 207x, muon to tau is only 17x. This suggests a smaller jump, maybe 10-20x, giving a fourth-gen lepton mass estimate of 1835 GeV. Hefty, but nowhere near the quark prediction. Okay, now for method 2. This uses the mass decay rate relationship derived directly from the theory's core principles. Remember, the theory posits that mass m is inversely proportional to coherence, c, and decay rate is also inversely proportional to coherence, R1c.
Right, R1c and R1c.
Which logically implies a direct proportionality between mass and decay rate.
Oh.
Simply put, the more massive and less coherent a particle is, the faster it decays.
Makes sense. Heavier things fall apart faster in this model.
Precisely. So we use the top quark again as our benchmark, since it's the heaviest and least stable one we know. We know its mass, m top equals for dV, and its decay rate, a top a 1.41 dV. Now, a fourth-gen particle, being way more massive, around 23 TeV based on method 1, and thus much less coherent, should have a correspondingly way higher decay rate. We can estimate this rate based on the mass prediction. If fourth-gen 23 TeV, the direct proportionality suggests its decay rate for gen would be roughly 187.5 TeV. Now, here's the neat part. We can flip the logic. If we know the relationship μe, and we've estimated fourth gen 787.5 dV, we can calculate the mass from the decay rate. Fourth gen top. I'm pulling in the numbers. 187.5 dV, 1.41 dV, x 483 TeV. And remarkably, this calculation lands us right back at approximately 23 TeV. So as the source emphasizes, it's quite remarkable that two seemingly different approaches both point to a mass estimate of around 23 TeV for a potential fourth-generation particle.
That is remarkable. One looking at scaling between known masses, the other using the theory's internal logic about mass and decay, and they agree.
Exactly. This convergence strongly suggests that there's a coherent underlying structure in our model, and it provides significant support for the reliability and internal consistency of our theory. It gives us confidence that the 23 TeV figure isn't just a random guess, but emerges naturally from the framework in multiple ways. It provides a concrete target.
Okay, 23 TeV. An absolutely immense mass. What does that actually mean for how long such a particle could exist? And could we ever possibly find something like that?
Well, the implications are pretty staggering. First, as we calculated using method 2, it would have an extremely high decay rate. A mass around 23 TeV corresponds to a predicted decay rate of around 187.5 GeV. Compare that to the top quark's 1.41 GeV, it's over 100 times faster.
Hmm.
This implies an instability that's almost hard to fathom.
So it just falls apart instantly.
Pretty much, which leads directly to its ultra-short lifetime. Remember, lifetime is inversely related to decay rate, whereas the reduced Planck constant. Plugging in that huge decay rate gives an estimated lifetime of 4.67 other 10 seconds.
10 to the minus 28. I can't even comprehend how short that is.
It's almost meaningless on a human scale. It's much shorter than that of the top quark, which was already incredibly short, around 10 RLEs. This vanishingly small lifetime would make direct detection extremely difficult, as these particles would decay almost immediately after being produced. They'd be gone before our detectors could even register them directly. We'd only see the aftermath, the decay products.
Now, you mentioned earlier that science, especially theoretical physics, is iterative. You don't just land on the perfect model first try. You test assumptions, refine things, and the source material actually documents this process for the HHHCR-ToE, trying different ways to model coherence and seeing what mass predictions came out. Can you walk us through that? It sounds like a fascinating peek behind the curtain of theory development.
Absolutely. It's a really important part of the process, seeing what works, what doesn't, and why. Those initial simple illustrative values for coherence, like setting C0, 0.9, C0, 0.7, C0, 0.5, they're useful for explaining the concept.
Yeah, easy to grasp.
But when you try to actually fit them to the real-world particle masses using the theory's equations, like Kinger 1c, you run into mathematical contradictions. You can't find consistent values for the underlying constants. And that tells you straight away, as the source notes, that our initial assumptions for the coherence coefficients were too simplistic. Nature's pattern is more complex than just a simple linear drop. So the source then explores more sophisticated mathematical models for how coherence might decrease across generations. The first attempt used an exponential decay model, CNEN. This assumes coherence drops off exponentially with each generation n. By comparing the known quark masses, top-up ratio 78,000, charm-up ratio 580, and setting Cia essentially to 1 as a reference, you can calculate the implied coherence values for C and C, and then find the decay constant C.
Okay, so using known data to fix the model's parameters.
Right, and once you have that decay constant, 6.36 in this calculation, you can predict the coherence for a fourth generation, which is about incredibly tiny, 5 by 10 here. Plugging that C back into the mass formula, MUP C, resulted in a predicted mass of about 423 TeV. As the source points out, this mass is significantly higher than our previous estimate of 23 TeV. So this specific exponential model gives a very different answer. This led to a second attempt using a geometric progression model, Cn equals CRN1. This assumes coherence decreases by the same ratio R between each generation. But when you calculate the actual mass ratios, charm up versus top charm, you find the ratio isn't constant. It changes significantly.
So a simple geometric series doesn't quite fit the data either.
Exactly. But you can sort of calculate an average ratio R, 3.6 by 10n. Using this average R to predict C gives a value of about 4.6 by 10 arrow. Plugging the C euro into the mass formula yields a mass estimate of around 48 TeV. The source notes, this value is closer to our initial estimate of 23 TeV and suggests that the mass could be in the tens of TeV range, so maybe getting warmer. Then a third attempt explored a fractal scaling model, linking coherence directly to the generation number n via a fractal dimension, dmcn into Carrios equals Benger O df, which implies mass scales as m Benger O n df, using the up and charm quark masses n equals 1 and nu2 to calculate this fractal dimension, gives dfn 9.18.
A fractal dimension of 9, that seems high.
It does seem large, hinting maybe this simple power law isn't the full picture either. Applying this scaling to Engel 4 predicts a fourth-generation mass of only about 620 TeV, which, as the source notes, is again lower than the earlier 23 TeV, and suggests that maybe simple fractal scaling may not capture the complexity and that those sharp resonance decay thresholds cause more significant jumps than a smooth scaling law would imply. So what's the takeaway from all these different attempts yielding estimates from 600 GeV up to 400 TeV?
That modeling this is really tricky.
It is. It shows the complexity and the nonlinear nature of the mass hierarchy. Simple models don't quite capture it. However, the source concludes that the mass increase factor approach, just taking that observed 135x jump from the second to third generation and applying it again, provides the most consistent estimate, leading back to that 23 TeV figure. The convergence we talked about earlier really refers to the agreement between that observation-based scaling method, method 1, and the theory-based mass decay rate relationship, method 2. Both point towards something extremely heavy, around 23 TeV, and extremely short-lived. This whole refinement process just underscores that the underlying reality is likely tied to those complex hyperfractal and resonance decay aspects of the theory, which aren't easily captured by simple formulas. But the 23 TeV figure remains the most compelling target based on reconciling theory and observation.
Okay, so we have this compelling converged prediction. A 23 TeV particle that disappears in maybe 10 Yertings. It sounds amazing, theoretically, but how on earth do you even begin to prove something like that exists? How do you detect something so heavy and so fleeting? It seems almost impossible.
Yeah, you've absolutely nailed the core difficulty. It is an immense challenge. The source even calls them experimental challenges in detecting ultra-short-lived particles.
Hmm.
There are two main hurdles. First, as we discussed, the extremely high mass requires very high energy collisions. We need accelerators powerful enough to potentially create something that massive. We're talking energies potentially beyond even the current LHC capabilities, maybe requiring future machines or significant upgrades.
Pushing the energy frontier.
Exactly. And second, the ultra-short lifetimes make detection of decay products difficult. The particle itself vanishes instantly. All we can hope to see is the debris, the particles it decays into. And trying to reconstruct the original particle from that debris, especially when it happens so fast amidst the chaos of a high-energy collision, is incredibly tricky. But it's not hopeless. The theory does suggest several potential pathways, strategies for experimental validation, even if they're ambitious. The main approach would probably be searching for indirect signatures at colliders. We wouldn't expect to see the 23 TeV particle directly, but we could look for its unique decay products, its specific energy and momentum fingerprint appearing in collisions at next-generation colliders. Think the LHC Run 3, the high-luminosity LHC upgrade, or maybe even future concepts like the FCC, Future Circular Collider, or a muon collider. The predicted mass of 23 TeV gives experimentalists a concrete target for searches. They know what energy range to focus on and what kind of decay patterns might signal this new physics. Another angle is to focus on measuring coherence-dependent properties of particles we already know. The theory predicts relationships between coherence and things like decay rates and masses. So we could make precise measurements of decay rates and masses of known particles to see if they match the patterns predicted by the coherence model.
Looking for tiny deviations from the standard model.
Exactly, looking for specific measurable properties like lifetimes, decay constants, or interaction strengths that should correlate with the theory's predicted coherence coefficients. Finding such correlations would be powerful indirect evidence. And then there's the more direct, perhaps more dramatic possibility of probing coherence collapse thresholds. Could high-energy accelerators actually push particles beyond their resonance limits? Could we force a coherence collapse? If we could, we might observe whether new, heavier particles emerge and how quickly they decay right at those predicted energy thresholds. This would be a stunning confirmation of the non-linear nature of coherence collapse. And supporting all of this experimental effort would be simulations and modeling. We can build sophisticated computer simulations based on fractal scaling laws and resonance decay dynamics to predict exactly when coherence collapse should occur at specific energy levels. These simulations can guide experimental design, telling us the best places to look and what signatures to expect, offering crucial insights before the experiments even run. And what's really neat is how energy itself plays a role here. The theory suggests higher energy scales are more likely to induce coherence collapse and trigger resonance decay thresholds.
Which fits with what we see, right? Higher energy collisions make heavier, less stable stuff.
Precisely. It aligns perfectly with observations at accelerators like the LHC. We need high energies to create massive, short-lived particles like the top quark or the Higgs boson. This intrinsic link between energy and accessing these less coherent states provides support for the HHHCR-ToE's basic premise. It also implies that the resonance operator itself might be energy dependent. Maybe higher collision energies actively, quote, increase the rate at which resonance decays and coherence collapses. This gives us specific, testable predictions for particle behavior at higher energy colliders, where coherence collapse and new resonance decays might be observed. It suggests there's a whole new landscape of hyperdimensional physics potentially waiting to be uncovered as we push to higher and higher energies.
Right, and it's important to stress that this isn't just hand-wavy concepts. The HHHCR-ToE, as presented, is built on a specific mathematical framework. It aims to be quantitative, predictive, and ultimately testable against data.
That's absolutely crucial. A physical theory needs that mathematical rigor. And the source outlines several key equations that form the foundation. So first, there's the fundamental mass-coherence relation. mkcugh. This equation mathematically states that mass m is inversely proportional to both the coherence coefficient and the coupling strength to hypergravity gh, with k being some proportionality constant. Less coherence means more mass. Okay, straightforward inverse relationship.
Yep. Then there's the link between decay rate and coherence. Higgy-USEC, again, inverse relationship. The decay rate is inversely proportional to coherence. C, with God as another constant. Lower coherence means a higher decay rate, meaning less stability. The resonance decay model is also formalized. One example given is an exponential decay, CR, CE, BES, R, showing coherence C decreasing exponentially as resonance R decays. But crucially, the math also needs to incorporate those nonlinear collapse points at critical thresholds, R equals RDC, where coherence drops suddenly and dramatically. Hyperfractal scaling gets an equation too, for instance. CREU. This shows how coherence C might change with some scale parameter, according to a fractal dimension in NeoBE, reflecting that complex underlying geometry. There's also a symmetry breaking parameter proposed as mon-ZUC. This mathematically links the degree of symmetry breaking to the loss of coherence, 1-ZURE. Lower coherence, C peri C, and closer to 0 means greater symmetry breaking. And finally, the idea that coherence could be an eigenvalue problem.
This suggests that the allowed values of the coherence coefficient C might not be continuous, but quantized. They could potentially be derived as eigenvalues from solving some fundamental equation, maybe a modified Dirac equation incorporating hypergravity, or from a dedicated hypergravity Hamiltonian. Hypergravity, like say. This would make coherence a truly fundamental quantized property. Now, the source is also clear that this mathematical framework is still under development. It outlines several key areas needing further refinement to make the theory fully robust and predictive. This includes things like refining the resonance operator, or what exactly is resonance mathematically, a phase, a frequency, an oscillation, need precise formulation, formalizing nonlinear transitions, developing the specific mathematical functions, maybe from chaos theory like bifurcations or phase transition physics, that accurately describe those sharp coherence collapses between generations, clarifying symmetry breaking, explicitly linking the loss of coherence to the breaking of specific symmetries, whether they are hyperdimensional or something else, interaction with gauge symmetries.
Exploring how this coherence mechanism might indirectly influence the known forces and interaction strengths governed by standard model gauge symmetries. Detailed decay dynamics, deriving exact formulas connecting decay rates not just to coherence, or 101C, but potentially involving resonance strength and other factors, allowing for precise predictions. Unified mathematical framework, bringing all these separate pieces together into one single, consistent, rigorous mathematical structure. Empirical calibration, using the best available experimental data on particle masses, lifetimes, etc., to precisely determine the values of the constants, like K and ToE, and scaling laws in the theory. And hyperfractal modeling, developing more detailed and realistic hyperfractal models to better understand how hyperspace geometry might dictate coherence decay and resonance thresholds. So there's still a lot of mathematical heavy lifting to do to fully flesh out the theory and make it ready for detailed experimental confrontation. Hashtag outro and
So let's step back for a second. What does this all really mean for how we see the universe? This deep dive, I think, has shown how this HHHCR-ToE framework offers a genuinely, well, revolutionary way to look at something fundamental, the structure of particle generations, something we've observed for decades but couldn't explain. It seems to bridge some really significant gaps left by the standard model, offering this unifying idea, coherence with hypergravity, that could potentially change how we view mass, stability, and maybe the fundamental nature of reality itself.
Absolutely. And connecting it back to the bigger picture, that convergence on the 23 TV prediction for a fourth generation, that's incredibly compelling. Even if detecting such a particle is a monumental challenge, having that specific theoretically motivated target is huge for guiding future experiments. And it really makes you wonder, doesn't it, if evidence for that, even indirect evidence, is found, what else might this framework reveal? What other secrets might be hiding in hyperspace, connected through this idea of coherence?
Yeah, it really underscores how discovery in physics often comes from asking those why questions and then having the boldness to explore completely new theoretical landscapes, even if they seem wild at first. This HHHCR-ToE framework feels like a testament to that scientific spirit. It offers a clear and crucially testable explanation for one of physics' longest-standing mysteries. It doesn't just potentially deepen our understanding of particles, it really shows the power of thinking outside the box, of venturing beyond our current comfortable models.
And here's a final thought to leave you with. Consider this seriously for a moment. If the stability of matter, the very mass of the particles that make up everything around us, is fundamentally tied to how in sync, how coherent they are with some hidden, higher dimensional hypergravity field, what does that really imply about reality? Could it be that everything we observe, all phenomena, are just different degrees of resonance, different notes playing out in a vast, incredibly complex hyperdimensional symphony, all subtly striving for perfect harmony, perfect coherence?
That is definitely something profound to ponder as you look at the world. Every interaction, every atom, maybe just a tiny echo from a higher dimension, seeking its place in that cosmic resonance. Thank you so much for joining us on this deep dive into the universe's hidden generations.